In this video, we'll look at independent events in probability. Two events, A and B, are said to be independent if one event occurring does not influence the probability of the other occurring. So we'll unpack that a little bit more now. So mathematically, we have that A and B are independent if and only if the following conditions are satisfied. So the first one says that the probability of A occurring, given that the probability of B has already occurred, is just equal to the probability of A. And similarly, the probability of B occurring, given that A has already occurred, is equal to the probability of B. And then the third condition, which is equivalent to the other two, is that the probability of the intersection of A and B is just equal to the probability of A times the probability of B. As previously stated, the three events above are equivalent conditions for independence. And that means that if one of the statements is true, all of the statements are true, and the events are considered independent. To calculate the intersection for two independent events, we can use the following formula. So that one there is listed as number 3 on the list above. A really important note is that if it is not known whether A and B are independent, then we assume that they are dependent unless we prove otherwise. So we'll quickly go through some examples of independent events now. So some examples include obtaining two even numbers when two die are rolled, obtaining two tails when two coins are flipped, and the selection of two or more objects when they are replaced before successive selections are taken. Examples of non-independent events include winning a point and serving in a game of tennis, selections of two or more objects when they are not replaced before successive selections. Further examples of that are selecting two cards without replacements from a deck of cards, and selecting marbles from a bag without replacing them. So for this example, we're going to consider the sample space, the numbers 1 through 10, with events A, where A is the event 1, 4, 5, or 7, and B, where that event is 1, 3, 5, 7, or 9, and C, where that event is 2 and 7. So very quickly, we're just going to work out the probability of events A, B, and C, each occurring individually, because we're going to need those for our calculations later. So if we consider the probability of event A occurring, we can see that there are 1, 2, 3, 4 outcomes out of 10, and that simplifies down to 2 over 5 as a fraction. Next, we do the same thing for event B. So if we have a look at event B, we have 1, 2, 3, 4, 5 events over 10 possible events, and that simplifies down to a half. And then we also have the probability of event C occurring, which is going to be 1, 2 events out of 10, which simplifies down to be 1/5. Next, we need to look at the intersection between these events. So A intersecting B is equal to the set of, and we can see that 1 is common to A and B, and that 5 is common to A and B, and that 7 is common to A and B. So we have 1, 5, and 7, and that means that the probability of A intersecting B is 3 events out of 10. Now that we've got that, we just check and see if the probability of event A times the probability of event B is equal to that. So the probability of event A is 2 over 5. We found that before over here. And then we multiply that by event B, which is 1 over 2, and we find that that is equal to 2 over 10. However, that does not equal the probability of A intersecting B. So the conclusion that we reach is that they are not independent, or they are dependent events. For part B, we're going to see if events B and C are independent. So we're going to do the same thing as we did in part A, and we're going to look at the elements in B intersecting C, and that is equal to the list of. So inspecting the two sets, we can see that only 7 is common to both of them. So there is only one element there, which means that the probability of B intersecting C is equal to 1 out of 10. Next, we're going to look at the probability of B times the probability of C. And previously we found the probability of B to be a half, and we multiply that by the probability of C, which we found to be a fifth, which equals 1 over 10, which does in fact equal what we found before, which is the probability of B intersecting C. Therefore, we can conclude that these two events are independent. For part C, we're going to do the same thing and check if A and C are independent. So we start off by looking at the elements in A intersecting C, and we can see that in event A, 7 is common with the element 7 in C, but there's no others, so there's just one element, which means that the probability of A intersecting C is equal to 1 divided by 10. And now we're going to check if the probability of A times the probability of C is equal to the intersection. So the probability of A was 2 divided by 5, which we found previously, times the probability of C, which is 1 divided by 5, which gives us 2 divided by 25, which is not equal to the probability of the intersection between A and C. Therefore, we conclude that those two events are not independent, or that they are in fact dependent. Andy and Brandon are playing golf. It is known that the probability of Andy hitting a good drive is 0.5 and the probability of Brandon hitting a good drive is 0.3. If the outcome of Andy and Brandon hitting their drives are independent, find the following. So the first thing we'll do just quickly is work out how we can represent this mathematically. So let's let the probability of Andy hitting a good drive be the probability of A, which is going to be 0.5. We can also say then that the probability of Brandon hitting a good drive is the probability of B, and that is 0.3. So that's straight from the question. For part A, we want to find the probability that Andy and Brandon both hit a good drive at the same time. So the language here is important. If you have a look at the word and, that means that they both do it. So that is the intersection of the two events occurring. So we know that that is the probability of A intersecting B. And because we know that they are independent, we can find that probability by going the probability of A times the probability of B. So now all we need to do is substitute in what we know. So the probability of A is 0.5 times the probability of B, which is 0.3. And now we need to evaluate that, and that is equal to 0.15. So that there is the probability that both Andy and Brandon hit good drives at the same time. For part B, we want to find the probability that Andy or Brandon will hit a good drive at the same time. So again, the language is important, and this is saying Andy could hit a good shot, or Brandon could hit a good shot, or both of them could hit a good shot. So that is represented as the union between the two, A union B. And we can use the addition rule for probability to find this out. So the addition rule says it's the probability of event A occurring plus the probability of event B occurring, subtracted away the intersection between events A and B. So substituting in what we know, we have the probability of event A occurring is 0.5 plus the probability of event B occurring, which is 0.3, subtract away the intersection between the two events, which is 0.15, and we find that that probability is going to be 0.65 when you evaluate that. So that means that the probability is 0.65 that Andy or Brandon will hit a good drive at the same time. So after this video, you should be able to understand the mathematical definition of independent events. You should be able to give common examples of independent and non-independent events. You should be able to determine if two events are or are not independent using one of the three equivalent conditions for independence. And finally, if two events are independent, you should be able to calculate the probability of their intersection.